Sure. Thank you, Maziar.
All yours.
Thank you, Maziar, and hello, everybody. My name is Mehdi Bakhshi, and I have a PhD in civil engineering. I'm currently working with AECOM, and this is for the past 3 years that working as a tunnel engineer. The subject of this technical note that I'm presenting today is simulation of segmental tunnel lining with a focus of the structural, geotechnical, and construction aspects of segment design. You can find my email address here. If you can send me an email. Precast concrete segments are a predominant support method in tunnels bored with TBM or tunnel boring machine technique, both in soft ground and fractured rock. In one-pass lining system, segments provide initial and final ground support, and they provide required space for different functions. You can mention water supply, wastewater tunnels, gas pipeline, power cable tunnels, subway, railway, and road tunnels. They're also designed to control groundwater inflow. Before presenting various load cases for tunnel segment simulation and design, let's go over some of the terms usually used in this topic. As you can see in this system, is comprised of rings. These rings are connected to each other through their joints, and you can see them on this picture. Segmental lining system is comprised of these aspects, and you can see circumferential joints. They're connected using the bolts and dowels as equipment. Each ring itself comprised of several segments connected through the longitudinal joints by bolts. The outer surface of the lining in contact with the ground is called extratus. The inside surface is called intratus. Okay. Now let's look at these governing load cases. We focus our attention to present different load cases from time of segment casting in manufacturing plant to the final service design stage. Usually they're divided, these load cases, into 3 different categories according to the time order and also nature of the loads. You can see here production and transitional load cases, construction load cases, and service load cases. All of them will be discussed in the next slides. Please note that it's important to consider design procedure as an iterative process. It usually starts with assuming a segment thickness, concrete strength, and reinforcement, and then we check the design with respect to these load cases. Production and transitional load cases include all the loading stages starting from time of casting up to the time of segment direction inside the TBM shield. Segments are lifted in early hours, for example, 3 to 4 hours after casting with mechanical devices, or as you can see in the picture, usually using vacuum lifters in the plant. This load case is related by 2 cantilevers, which is loaded under its own dead weight. You can see in the schematics on the right side that cantilevers are used for this simulation. They're loaded under its own dead weight, and as you can see in the table, maximum developed bending moment is a function of weight and free length of the segment. Of course, the key design parameter will be 4 hours compressive strain and residual tensile stress, which is also referred to as sigma P at 4 hours. Segment storage is the next loading case which may govern. Segment storage happens right after demolding. So 3 to 4 hours strain should be used for this design. Usually all these segments comprise the full ring, which are piled up within one stack using the blocking support. Focus of the design should be on the bottom segments. The reason is that it will be possible to have dead weight of the above segment eccentrically applied on the bottom segment. As you can see, this load case is simulated by simply supported beams. This eccentricity can be placed outside or inside these wood blocking. Maximum developed bending moment depends on location of wood blocking and eccentricity. Again, key design parameters would be early age, like 4 hours, compressive strength, and residual tensile strength parameter, especially for the fiber reinforced segment. Next loading case is segment transportation. Segment transportation from stack yard happens after 28 days, or when 28 days strength is achieved. Similar to a storage load, this load case simulated by simply supported beams loaded on its own self-weight. At eccentricity, dead weight of above segments are considered, but there's a difference. The difference is that usually half of the ring segments are transported within one stack. And you should also consider that you choose a dynamic shock factor has to be considered in this load case. Let's shift to segment handling as another governing load case. Handling from stack yard to trucks or rail cars usually carried out by a special device as vacuum lifters, sometimes slings. For the first two cases, I mean the special devices and vacuum lifters, simulation with cantilever beams are used. You can see them in previous 2-3 previous slides for the case of demolding. But for the case of lifting with the slings, as you can see on the schematic on the right side, maximum developed bending moment is given in the table. Again, a dynamic shock factor has to be considered for the handling load case, and design parameter are 28 day specific compressive strength of concrete, and in the case of fiber reinforced, a residual tensile strength at 28 days. Now let's take a look at construction cases that start from the time of segment erection inside TBM shield up to the time when installation of a ring is completed. And also the annular space, of course, between the segments and the ground. I'm sorry. Between the annular space between the segment and the ground is filled with the grout, and grout is hard. Okay, we start with TBM thrust jack force. If you look at the above figure, after assembly of a complete ring, TBM moves forward by pushing its jack on circumferential joints of newest assembled ring. In the below picture, you can see developed stresses. Compressive stresses are developed right below jack shoes. You can see that in the picture in gray area. Bursting tensile stresses develop deep inside the segment, and spalling stresses developed very near the surface between the jack shoes. Of course, in this picture, you just see one jack. So also it happens between the jack shoe and the segment edges. Different analysis methods are available for this load case, including simplified equation, analytical methods, and finite element analysis in 2D or 3D. Let's start with simplified equation for TBM thrust action using ACI or DOB formulation. ACI 318 formulation for post-tension anchorage zone can be used here for simulation of bursting forces. German tunneling committee, referred to as DOB, similar to ACI, recommends simplified equation that is shown in this slide. They are pretty much similar. Some few the difference between the two methods that I can mention is the location of rebars that DOB recommends in 0.4 HS instead of ACI, which recommend H, 0.5 H. Other than that, pretty much similar equation with both methods. The famous analytical method for TBM thrust action is Inger diagram that usually gives more details of bursting forces. Here you can see distribution of stresses, and then key parameter here, similar to the simplified equations, are dimensions of loading surface, which is in this case is the jacking area, and dimension of the spreading surface inside the segment, which could be the whole segment, or if there is an eccentricity, less than the whole segment. Based on such diagram, you can find tensile strength, tensile bursting strength as a function of fully spreaded compressive strength. And you can find the location of the maximum stresses. 3D finite element simulation have advantages versus previous methods. Simulation is more accurate, and the reason is that the nature of these stresses are 3D. And another key advantage is that it's possible to determine spalling stresses using this method. Usually two adjacent rings are modeled with solid elements. As you can see in the picture, all translation or degrees of freedom behind prior segments are fixed. The two segments are connected by link elements, and recesses between two segments can be modeled. On the front face of the newly assembled segment, you can see thrust forces applied only on the contact area of the present segment. Another advantage is that you can also simulate the maximum gasket reaction force that are applied on the gasket groups. Here you can see a typical result of 3D FEM simulation for TBM thrust action. As you can see in the left picture, tensile stress contours show significant spalling stresses near the surface than bursting stresses inside. On the right-hand side in the picture, you can see developed compressive stress. These stresses are compared with respect to the compressive strength of the concrete to make sure that the concrete does not fail. The next loading cases that we are reviewing here are backgrouting pressure. Backgrouting is performed to fill a tailwater that created between the ground and the tunnel lining. Usually simulated in two-dimensional by a solid ring shown below, and grout pressure at the crown is slightly higher than groundwater pressure. There are some models to come up with the exact numbers that I didn't go through details, but they are available. Invert ground pressure is usually calculated by the equilibrium between the grout pressure, total grout pressure, dead weight, shear stress of semi-liquid grout that we usually consider between 20 to 100 Pascal. According to this method, radial pressure that applied is linearly distributed. And what you can see on the left-hand side of that picture, for example, for such a large diameter tunnel, the grout pressure on top is 225 kilopascal, linear increasing, reaching 245 kilopascal on the spring line and 264.5 kilopascal in the invert. Actual forces and bending moments are shown, as you can see on the middle and the right picture for the case of large diameter tunnel. Secondary grouting load case is also considered. This grouting, which is called check grouting as well, is performed when there is an annual gap exists between the lining profile after grout is hardened. It's performed by radial injection through holes that provided in segments, and they are usually simulated in 2D by solid rings. In this case, since the grout is hardened, there is a full contact between the segments and the ground, and therefore the interaction with the ground is modeled by radial springs. Ground pressure applied with a triangular distribution. This is a recommendation by ITA, International Tunnel Association, that for the example in the case on the left side, you can see a maximum grout pressure of 225, which was for the previous case, distributed triangularly over 36 degrees on this ring. Actual forces and bending moments developed are shown here, which are significant. Now let's move to service load cases. Load in the final service stage is usually presented by long-term interaction of the line with the ground and groundwater. This is almost the most significant loading case that has to be considered for design of tunnel linings, especially segmental tunnel lining, and recommended analysis and design methods are elastic equation method, beam springs method, front element method simulation, and also discrete element method simulations will be discussed in the next few slides. Other methods that I will not cover in this presentation, but also very acceptable, are Muir, Bruce, Curtis, Dudek, and Erdmann, and empirical method of Peck. Please note that since we are designing segments for ultimate and serviceability limited state according to LRFD method, load combination factors such as this table can be used. This is actually AASHTO recommendation for loads of dead weight, groundwater pressure, vertical ground pressure, horizontal ground pressure, and surcharge load. Okay, elastic equation method is recommended by International Tunnel Association, ITA, and Japan Society of Civil Engineers. As you can see in this figure on the left side, distribution of the loads used in this method are as such, and due to such distribution of the load, on the table on the right-hand side, you can find the equations for calculation of member forces. Results of this analysis are shown in this slide. You can see that this is for a case of a large diameter tunnel again, with overburden of 3 to 4 D, which is the diameter of the tunnel. As you can see, actual force does not change significantly around the perimeter of the tunnel, but bending moment changes from 0 to high values of 1/3 kN. Is another famous method used for ground and groundwater load case analysis. This is recommended by also JSCE, AASHTO recommends that, and Austrian Society for Concrete and Construction Technology, OVBB. It's usually modeled by segmental double wings, as is shown in the left figure, and you can see that ground interaction is usually modeled by radial, tangential, and longitudinal springs. Interaction spring stiffness can be calculated by different or determined by different methods, but usually in U.S. tunneling industry they use a U.S. Army Corps of Engineers formula. Also, segments and ring joints are modeled in this method by the springs. Here you can see typical results using beam spring simulation for, again, a large diameter tunnel. Results very similar to elastic equation method. Actual force again does not change significantly around perimeter of the tunnel, and of course bending moment changes from 0 in some cases to high values of 156 kN/m. Another very important method of analysis is discrete element method, FEM simulation. These are usually recommended for tunnels in fractured rock, and the reason is that 2D discontinuum analysis has to be performed for investigation of interaction of the joint sets of intersection. Usually intact rock and joint set properties are used for such DEM modeling, and as you can see on the right side, that's a graph for the bending moment developed in the segmental lining system. Bending moment distribution is completely different than in the soft ground. Here we show results, the method for 2D FEM simulation. These methods are also recommended by Austrian Society of Concrete, called OVBB, and then French Tunneling and Underground Engineering Association, which is referred to as AFDES for the soft ground. 2D continuum analysis with FEM usually sufficient if the tunnel doesn't have any sudden change in cross section or there is no concentrated load intensity. The advantages include, but of course not limited to the one that I'm going to mention. One of them are you can actually consider behavior. So load distribution result from lining deformation is possible. Of course, we can consider excavation stages, one of the very major significant advantage of this method. And also, this method is valid for non-uniform and anisotropic initial stresses. For example, if there are several different formations of ground or external loads because of nearby existing structures and so on. Here you can see typical result of 2D FEM simulation. This figure shows for actual forces and bending moments for a large diameter tunnel. Again, results are very similar to both elastic equation and beam spring method. As another major method for analysis of ground and groundwater pressure are 3D FEM simulations. This is also recommended by OVBB for tunnels in soft ground. These methods are appropriate for simulation of tunnels in special areas, such as areas of intersection between if there is any crosscut and main tunnel. Such an example is shown in the below picture on the left side. You can see penetration of a very long adit into a large diameter tunnel that has to be simulated with 3D FEM analysis. On the right side, you can see another case. This method also very appropriate when external loads are present because of nearby existing structure. By meaning that we can mention like other tunnels and bridge piles. On the right side, if you consider the red tunnels as existing tunnels for existing structure, we are designing the below tunnels which are shown in blue. In 3D FEM simulation, it is important to talk about volume loss concept. Usually there are generally three types of volume loss that we consider. Face loss, which happens ahead of excavation phase. Sheet loss, which happens usually because of the conical shape of shield, and because of that the ground tends to slip and deform along the shield. Also there is a tail loss behind the shield, which is filled by grouting. One of the main advantages of 3D FEM simulation is modeling this face loss, which is only possible in 3D method. Now let's look at typical result of 3D FEM simulation. This figure shows induced system and compressive at the crown of the existing tunnel because of the construction of the twin tunnels. For the case that's shown in 2 slides before, the distance between the design tunnel here and the existing tunnel above that is 5.5 feet, for example. Stress are compared with the strength of lining for design checks. Here you can see typical result of 3D FEM simulation for a penetration of a long adit into the lining. As you can see in this element 3, in this simulation, 3 segments are removed. And then after, induced axial forces and bending moments are used for design check. Another load case is longitudinal joint bursting forces. This load case is very similar to the load case of TBM action. Here is maximum axial force and bending moment developed from ground and groundwater loading case. Only longitudinal joints are used. Because we're considering our attention, we're focusing our attention only on the longitudinal joints, it's good to get these axial force and bending moments from the result of models such as beam springs. And bending moments is basically analogous to eccentricity if we consider that the ratio of the bending moment over actual load is the eccentricity that can be applied. Again, we can use a tension block concept and use ACI or DOP method, as you can see on the top right-hand side. And then other available analysis of design methods are FEM, such as what is shown below, and again, Anger diagram can be used in analytical method here. Another load case that we consider is loads induced to additional distortion. This is a special load case recommended by some of the standards. One I mentioned here is Singapore Land Transport Authority, we call NTA. During assembly, because of some of these joint connectors may yield, or it might be like excessive grouting pressure, or even in service. If we use elastic equations, we don't consider like construction of adjacent tunnels. But in FEM, it might be possible, but using like other methods may be not possible. So we have to consider that differently. Morgan formula is very much appropriate for this purpose. So having all those embedment, bending moment, we can add an additional distortion moment, such as what is shown here, which is a function of the concrete Young modulus segment moment of inertia, diametrical distortion, and radius of the excavated tunnel. Another and final load case that we consider in this presentation is special loading cases. This may include earthquake, finite pollution, breakout, and excessive longitudinal bending moment. Different seismic analyses pertaining to tunnels are shown on the right side. Those are usually overlaying actual and curvature deformation analysis that can be used, performed using a beam spring model, for example. And for example, for the case of fire load, we can simulate such load case with the temperature gradient between the intradas and intradas of the line. Also, it's very usual to explore by increasing radial pressure at the service condition. For example, if we have such radial pressure already for embedment loads, we can add another 1 bar or like 3.5 psi to the radial pressure and rerun the analysis and then check the developed bending moment and actual forces. After determining actual forces and bending moments developed, because of all these different load cases I just presented, it's needed to check them with respect to actual force bending moment interaction diagram. That's the tool that we use for design at the last stage. For example, here you can see a design check performed by Andrew and Chappell in 2008. For some of these load cases that we discussed, not all of them. But as you can see in this figure, the strength of the plain concrete segment is not really sufficient for studied load cases, especially for the load case of stacking and handling, and then also for the load case of transportation. But you can see that a fiber reinforced segment can take these internal forces. Now that we mentioned fiber reinforced concrete segments, let's have a brief talk about these segments. Fibers are recently used as a totally or partial replacement of steel bars for reinforcement of concrete segments. Basically, you can use a plastic rigid constitutive law, which is shown here at the top right figure, for FRC segment modeling. You can see a distribution of the stresses on the bottom figure. From left side, you can see a section, then a strain distribution, and then a stress distribution. Using these constitutive law, parametric study is shown on the right-hand side. You can see the effect of fiber dosage increasing from 20 to 50, and by that actual force and especially bending moment capacity is increasing from inside and getting close to reinforced concrete. Some of the key references I show here are shown in these two slides. These first 1 and 2 slides are for external references that we considered for making this presentation. We also have used our own internal references. Most of these papers are written by myself and co-authored with Dr. Vergan Nasri from AECOM as a chief tunnel engineer. And with that, I would like to conclude this presentation and thank TNO Diana for giving me such an opportunity to present this webinar, and also thank you for attending this webinar. If you have any question, we can go over them one by one.
Well, thank you, Mehdi. It was very interesting, and you highlighted the key factors in terms of the manufacturing and say handling, and indeed putting things or these lining segments into the real projects. But before we conclude, I want to quickly go over some of the application projects that we may kind of consider based on the real soil structure interaction and effect of tunneling TBM in a real projects. I quickly highlight some of the examples because with the DANA program you can simultaneously consider both effects in terms of the underground structures or complex underground structure tunneling, and at the same time the superstructure. This could be existing buildings or foundations, or even some sort of combination of that, including pile foundation and the superstructure. So this is one of the examples that I would like to highlight here, the combination of the masonry structures on the top surface building and different sequences that you're going to consider for advancing underground tunnel. So the effect and the impact of the settlement due to this tunneling is very important in terms of monitoring the induced cracking damage in the superstructure. So the simulation here conducted in a way that basically either you consider the whole excavation process in one go or based on the segmental excavation and reinforcing the inner tunnel, and how you can control that effect on the superstructure. So here you can see the induced cracks on the top building. Similarly is in London, that's another, say, extension for tube or say underground tunnel. And here once again the effect and impact of the TBM tunneling monitored with construction stage analysis, and because the position and this line is under this masonry structure, they wanted to see what are the possible damage that could cause for this heritage type of building. So you can see the level of the settlements, the induced level of cracks in the model. And one more thing that Mehdi mentioned correctly in his presentation is the effect and impact of the fire, and especially these days all the codes and design aspects and authorities are asking for checking the fire analysis on the structures. So once again in DNA you can combine all these effects including say structure of the tunnel lining, reinforcement part. This could be say steel grid or could be fiber reinforcement. So depending on the type of material that you're going to use here, you can characterize that based on the say effect of fire on them, so material degradation, the induced level of the fire, and how the material gonna lose their strength. There is one more thing here is the soil structure interaction. So we define a kind of interface between the tunnel lining and different soil layers here to cover the full interaction between the nonlinear behavior of the soil and nonlinear behavior of tunnel lining, because this fire gonna induce series of say expansion loads in the model, while the whole model from the top surface is subjected to the traffic load. This is I just want to highlight here is one of the high-speed underground train tunnels, and the authority were asking for effect and impact of the 2 hours fire inside this tunnel. So performing this fully transient and say coupled analysis between the thermostress analysis and the effect of that in the say structural from the initialization and then placing of the lining and inducing the or mimicking the fire effect leads us to the point that how this temperature varies in gradient in the thickness of this tunnel lining, and how this could cause damage and cracking in the tunnel segment. This is very important because you can see here the temperature by itself, it causes some expansion, so model kind of heaves. But on the other hand, from the top surface there is traffic load, and these two locally cancel each other. And here you can see the say the profile of the deformation due to development of the temperature up to 2 hours. In the next slide you can see the development of the cracks in the model. So how these cracks are initiating and propagating after 2 hours, and the resultant stresses in the reinforcement, or if you're using, say, fiber reinforced concrete, then based on the characteristic curve that you're going to get from manufacturer, you can get the level of induced principal stresses that are causing, say, failure in your model. So thank you again for your attention. With Mehdi, we are available to answer your questions. You can freely type in the chat box. If you would like to have a live conversation, please let me know. Then I can unmute your, say, microphone. Then we can have a live chat.